Hi, I'm Rich with insideHPC. We're here at the Intel HPC Developer Conference in Salt Lake City, and I'm here with Mustafa. How are you doing today, sir?
I'm doing all right.
Great, great. Well, hey, I understand you had a talk today. Could you tell us what that was about?
So the talk today was about optimizing deep learning workloads and frameworks for Intel architecture, Xeon and Xeon Phi, and in general just what the challenges that we went through and the upside to optimizing these frameworks for end users.
Okay. And so are these like open source kind of frameworks that you're taking and tuning for the Intel architecture?
Absolutely. These are open source leading frameworks from the ecosystem, like typically big players like Google and academia, like, for example, Caffe from Berkeley and so on.
Okay, so things like Tensor and Caffe.
TensorFlow and Caffe, and Theano and Torch and other frameworks.
Okay, I mean, the interesting statistic I heard yesterday is that there's 2 of these coming out every month, brand new ones, right? They're sprouting up.
Yes, so I haven't really looked this year, but last year we did some statistics and we were seeing roughly a new framework every 21 days on average in 2015.
Okay. So this is definitely a hot area for developers, this deep learning, this machine learning kind of thing. Where is your focus? Is it trying to get it to scale, go faster, or where are you at?
So we're focused on 2 things. We're focused on getting single node performance up to what the hardware can deliver. And there is huge upside we're seeing from an optimized out-of-the-box code versus optimized or even partially optimized. We're seeing in certain cases 40 times better performance, 200 times better performance depending on the workload and topologies. So the message to developers is do not be fooled by what you see out of the box if you're using an optimized. The upside of that is if you optimize, if you do simple things like just pick the optimized version of these frameworks, or even recompile, or even do a little bit of change to use MKL, for example, your upside is not 20%, it's not 30%, it's dozens of times better performance, and sometimes hundreds of times better performance. That is the key message to developers. And the other aspect of it is once these are optimized for one generation of Intel hardware, the effort is going to be a lot less going forward. It is somewhat of a one-time effort, and then it becomes like high-performance computing, where every generation you do some further tuning on the same applications. But by and large, it is going to be a one-time effort. And again, the upside is huge because these codes were not quite written quite for IA. The other conclusion that we saw is there is nothing fundamentally in these frameworks that make them, or in this line of workloads, in this segment, deep learning and deep neural networks and artificial intelligence in general, there is nothing fundamentally in these algorithms that makes them less friendly to IA or even other architectures. Once you optimize, it becomes really a peak flops comparison. It becomes which architecture delivers the peak flops, and even generation to generations, how much peak flops is what you would expect in terms of speed up.
So when we talk about machine learning, there's the 2 sides, right? The inference and the training. Where are you focused?
We're focused on both. And the reality is that, just to go a little bit more technical, the training for these neural networks for artificial intelligence workloads means you basically go ahead and learn by doing. You say, in inference, I'm going to be predicting certain things, like predicting what this is an image of, or doing artificially the translation between 2 languages, which means I predict what this thing said in French means in English, or in Arabic means in Chinese, or something of the sort. What you do in training is you learn by doing. You start predicting and see how close you are to the answer, and then based on that, you update the function that you are using to predict effectively. So inference is a subset of what you do in training, which means a lot of the optimization that you do for inference will carry forward to training, and vice versa. When you optimize for training fully, you optimize the forward pass, which is basically the inference pass, and we're looking at both. We have a lot of focus on both platforms. At the corporate level, we have a lot of focus on both.
What kind of uptake are you getting? I mean, there's a lot of developers here. What's the feedback you're getting about Intel's efforts here?
This is only my personal feedback, so I'm sure we'll probably have more insights once we start collecting from different places. But there seems to be a lot of interest. We had a lot of people in the talk earlier today, and the questions were also clearly engaged, and people who have been trying to extract performance on IA from these frameworks, from deploying these frameworks. And this is not surprising. HPC is a lot of data. HPC is a lot of data, and this is what deep learning and machine learning in general can extract value from, is huge amounts of data. These algorithms are designed to extract insights from a huge amount of data, and cloud was earlier in that space, but certainly HPC seems to be following suit fairly quickly.